So thank everybody for coming to this month's AFSIG meeting. For those who may be listening on the recording, this is the Tucson Astronomy Association's Astronomy Fundamentals Group. This is our regular monthly meeting. Tonight we have two presentations up on the road. One, our starting presentation will be by Pete Hermes, who will be doing a light presentation on the ancient Greek astronomer Ptolemy. Following up that, Doug Smith will be giving a talk on lunar craters, which will be interesting for anybody who likes to do lunar observing. Also probably learn some cool things out of that as well.
Hope it's interesting for other people too.
Yeah, always something cool to learn there. Without any more delays, Pete, we will toss it over to you.
Okay, thank you. Everybody see the first screen of the presentation?
Yes.
Yes.
Okay.
Yes.
Very good. I'll have my cursor move around occasionally, but not a lot. Hey, thank you for the opportunity to present tonight's presentation on Ptolemy, probably one of the, well, not necessarily the first, but probably the first or second astronomer going back to ancient times of note. I think most people are familiar with Hipparchus. Hipparchus actually preceded Ptolemy. In fact, he used some of his information, some of his ideas that he carried on. But essentially, Ptolemy is probably one of the most well-known going back. You mentioned that he is Greek. Yes, he has Greek roots in his name. More than likely, his ancestry was Greek. And in fact, when when we talk about him today, let's see if I can get my screens to advance. Dun, dun, dun. There we go. Anyhow, just really two aspects that we're going to talk about tonight: his life and his work. Typical of most individuals, even of that were known through history, there's very little about his life. When we're going back almost 2 millennia, 2,000 years ago, when he first started, essentially you'll see a number of dates, but for the most part, he was probably born somewhere around 100 CE, Common Era, or AD, however you want to look at it, and probably lived anywhere from 68 to, in some cases, I've seen dates up to almost 80 years old, and I find that kind of hard to believe for someone in that time, but maybe he was one of the exceptions. Any of the pictures you saw, like on the first slide that I have, and on the second one, as far as actual renderings of pictures of Ptolemy himself, these probably are not necessarily accurate. I don't think there were necessarily any images that were memorialized on paper or some other medium. These are more or less just personifications of probably what was drawn up in the Middle Ages, the middle of the second millennium. But for the most part, Ptolemy, we're not sure where he was born. It's pretty assured through the history that he died in Alexandria. And you can see a small map there of Roman Egypt. There wasn't a whole lot to it. And like I say, during this time, Egypt was under Roman rule. We'll get into a couple of the roots of his name. But of course, you can see Alexandria up there pretty much on the western end of the Nile Delta. And there's one other place I want you to keep in mind, which is real close to Alexandria. This will come up towards the end of my presentation, is Canopus. Basically in the same area. We're not too far from where he probably passed. But like I say, we'll work on his life a little bit, but more so, of course, what he's more known by, rather than particulars in his life, are some of the works. He had some pretty substantial works. There's one that he's very well known for, dealing in astronomy, and a couple of others, both in cartography and astrology. Believe it or not, of course, back in those days, astronomers, astrology, there was a certain mix there, but he makes an important distinction, and I think this stands out a little bit, and much to his credit. Okay, basically his life. Claudius Ptolemaeus, you see, basically has a Roman first name, Greek last name. He's probably of Greek heritage. But for the most part, this is his Latin name. More than likely, he was probably a Roman citizen due to that being granted to one of his ancestors, either by one of the emperors, Claudius or Nero, who preceded in the previous century. Here again, you see a number of dates, basically the length of his life starting in 100 CE or AD up to 170. And the other sources will list derivations on that, going back even 15 years prior to that and up to 168. Like I say, in this one, you see that middle source 90 to 168, 78 years of age. That would be pretty good for an individual during that time period. For the most part, not quite sure where Ptolemy was born, but we're pretty sure that he died in Alexandria, which would be Greek or Hellenized Egypt under Roman rule at the time. I mean, there was a lot of Greek and Hellenic influences in Egypt preceding this time period up through the Roman rule. Pretty sure that he lived most of his life, and like I say, more than likely died. Major areas of study that Ptolemy undertook, he was a mathematician, an astronomer, an astrologer, a geographer, and a music theorist. I'm not going to get too much in the music theorist aspect, but basically, I'll just mention the fact that one of the things, of course, he tried to do with harmonics, tried to marry up a little bit with some of his mathematics, even though most of his work in mathematics wasn't really necessarily pure mathematics, but more or less along the lines of trigonometry with respect to some of the models he had in astronomy. For the most part, he wrote in ancient Greek. A lot of the ancient Greek manuscripts didn't survive. Some of his works subsequently were translated into Arabic and in some cases Latin. Some of those did survive, but generally they were compilations that were done many hundreds of years after his life. And so it's somewhat difficult trying to source some of these original documents because a lot of them just didn't survive. But for the most part, like I say, wrote in Greek, and used a lot of data from other individuals, principally with respect to astronomical data. It was from the Babylonians and the Islamic areas off to the east of Egypt. That's where a lot of that came from. And subsequently, a lot of that information that he compiled, of course, survived and was used by Western Europe up until the point the Middle Ages, when the models of the sky, the heavens changed somewhat substantially. But basically, this is all that's known about him. Was he married? Don't know. Did he have family, kids? How large was his family that he came from? We really have no idea. We have a couple of ideas of individuals that he might have been associated with respect to learning in some of the disciplines that he concentrated in. For instance, there's this Theon of Smyrna, who was likely one of his teachers. Not exactly the most scholarly individual, but for the most part, being that Ptolemy was in and around Alexandria, of course, he had access to, probably one of the most extensive libraries in the known world at that time. And then the other individual, Cyrus, wasn't necessarily a teacher, could have been, but most of the sources suspect that he might have been one of Ptolemy's contemporaries. But nonetheless, they don't identify necessarily any projects or any work that they would have done together. But these were two individuals that were identified as having somewhat of an influence in his life. And by all means, if anybody has any other additional information, corrections, please speak up. The preponderance of Ptolemy's work and effort, of course, was done in astronomy. And that was probably, I won't really want to assign a percentage to it, but if I was to make an estimation, at least a half, if not more. He spent quite a bit of time in astronomical observations for about, I think I have a time period there of about 15 years. A lot of his work was based on what Hipparchus had done preceding him. Hipparchus, one of the first to combine math for predicting astronomical events with qualitative geometric models. Basically Ptolemy, followed through and continued a lot of this work, but very heavily involved in his, in the models, the geometric models, especially the nested spheres, and of course trying to present them on a single plane. That was a lot of his work. You can see one thing that we do know based on the records that he compiled with respect to his observations. And we know he was at least alive and working during this period. Now, granted, the calendar has changed subsequently, but for the most part, his first documented observation was made on March 12th of the year 127. And his last one, at least of note, documented, was on February 2 of 141, so 14, not quite 14 years later. I mean, undoubtedly, there was a lot of work on either side of that. He probably lived for another 20 to 30 years after his last observations. I doubt those were his last, but these are the ones that records survived with respect to that were, picked up in the Middle Ages and passed down into later works, of course, then, when printing came around. And this is one of the things we have to deal with, given that, there isn't a whole lot with respect to, you had manuscripts, but you had basic original manuscripts, some were copied, but there wasn't a whole lot of them. It wasn't like in the Middle Ages when the printing press, eventually came around and there was wholesale movement of written material. Yeah, there was written material back in, ancient times, but it was somewhat limited. And of course, in some cases, a lot of things didn't survive. I saw the comment with respect to the destruction of the library at Alexandria. And I'm sure that, a lot of things, I don't know if any of his work was necessarily lost, but I'm sure that there were a lot of things that were lost. And of course, one of the things that he is probably most well known for with respect to astronomy is his geocentric models. Ptolemy's, work and basis, and this came from, prior, I think Aristotle. I don't necessarily know if he first came up with the idea, but this was derived from Aristotle. Aristotle had the belief, and I shouldn't say belief, as far as his knowledge at that time, he understood that the Earth was at the center of the universe. So did Ptolemy, and he constructed a lot of his models, a lot of his math working towards trying to verify the modeling that he'd done with respect to Earth being at the center of the universe, probably followed by the moon, and I think maybe Mercury and Venus, and then the sun, and then Mars. And beyond that, there were the stars, and that was the outer sphere. But with respect to the planets, I think Mars was about it. You'll see this when we get to one of his other works as far as the breakdown of the various books. One of the other things that Ptolemy was, spent a lot of time where we're constructing these tables that were used, that could be used based on previous observations and his own to identify the position, for the sun, the moon, and the planets that were known at the time, and the rising and setting of stars and eclipses, the very basic, astronomical information. And he was able to establish these tables that showed when they occurred in the past and when they were likely to occur in the future. Nothing was perfect here. These were estimations, but for the most part, the math was fairly sound, at least for this time. Major contributions throughout his lifetime, even outside of astronomy, of course, the Almagest was his major work. Mathematiques and Taxis, the great treatise, had 13 books in there, and I'll show you the breakdown. But that is probably the one work that he is most well known for. Not necessarily a lot of people were familiar with this. For about the first 1500 years, this is a document that basically was the foundation for astronomy from his time up until the Middle Ages. And not necessarily a lot of people understood it because they didn't have the mathematics or understood the mathematical background and basis that he had put forward in this. He also did some work in geography, basically some cartography work with respect to the known world, which was pretty much Northern Africa, and you'll see a representation of the map, but basically the Roman Empire at that time, and then out east through, the central parts of Asia. A lot of his information was developed by Byzantine and Islamic scholars and astronomers prior to him. And of course, the work product that he put out was a basis for a lot of Western European science with respect, especially to astronomy and some of the other areas that he worked in subsequently. Going back to the Almagest, this was, a sole comprehensive work of astronomy from ancient times, one of the most copied, and it pretty much held as the principal work all the way up until the Middle Ages, so almost basically for 1,500 years, which is pretty amazing that this one document, this one piece of work was able to basically pretty much form the basis of, any astronomical work that, going back to the early part, going back to ancient times all the way up to the Middle Ages. Contained a star catalog. Portions, of course, were originally created by Hipparchus. This was follow-on work. It was very typical. You even see this going back a couple of hundred years, but it was very typical for scholars, writers, anybody that was doing work. They would base it on someone else's. Attribution wasn't as important back then as it is today. In fact, in some cases, using someone else's work was considered somewhat of an honor. Of course, nowadays, when people put up their own pieces, they want to make sure and attribute any prior sources. But needless to say, there's a lot of information and data out there, and certainly Ptolemy made use of it, especially past data, to build his tables up for the predictive, positions of the heavenly bodies later on. It's pretty much theorized that the Almagest was completed about 150 CE, so somewhere between 15 and 20 years before Ptolemy died. One of the things that it contained were the 48 constellations that form the basis for the current 88. Here again, a lot of that I think was developed by Hipparchus, and it was carried on. That work was carried on with Ptolemy. The big thing that Ptolemy did with respect to the Almagest as far as astronomical information and data was, this publication contained a lot of tables that incorporated being able to identify the positions of the planets in the past or in the future, and some of those other events that I mentioned previously. The Almagest in here for just for if anybody's Greek and they can read that, the first thing you see in the parentheses is the Greek title, and then the Almagisti would be the Arabic, the phonetic sounding Arabic version. Of course, it's not an Arabic lettering, but typically these were the languages of the day. And like I say, I think most of Ptolemy's works were originally, as far as his work, were originally published or put down in Greek. But anyhow, here you see the 13 books that were contained within the Almagest. The first book, Cosmology and Trigonometry, lays down, the mathematical and trigonometric basis for some of the things that he presented in his treatise. Then moving on to spherical astronomy, and then he covers the main heavenly bodies that were known at the time: the sun, the moon, eclipses naturally to talk about, fixed stars, Mercury, Venus, and Mars. Jupiter and Saturn, I don't know if he necessarily, did that work specifically with respect to those bodies, or he had something else out there that was seen. I'm not too sure that this was very specific, but it is, is one of the books that's mentioned in there. I'm not too sure that he might have necessarily identified them. They were big enough to be seen, surely, but as far as their basic motions and whatnot. And then, of course, he gets into retrogradation, which explain some of the anomalous movements, especially the outer planets, Mars, Jupiter, and Saturn, as the Earth went around its rotation, which was one of the more basic things that was difficult to explain with his geocentric modeling of the universe, let alone the solar system. And then planetary latitudes, talking about different locations on the Earth and how things would show up differently depending on where you were at. Other works in astronomy, the Analemma, which was a short work on sun location correlated with declination of the sun, terrestrial latitude and hour. Basically, the figure, the figure 8 that the sun will scribe in the sky at the same time during the day as it moves through the course of the year. Doug, did you want to add anything about this? Anything you know about Ptolemy with respect to the Analemma?
No, I know he did it. I know that. And he was just following the work of the ancient Greeks long before him.
Yeah.
Aristotle and Eratosthenes.
Right. And then we have the basis, rising to the fixed stars. As with all the other bodies, this specifically addressed the stars. Here again, going back to ancient times, they didn't have telescopes. Everything basically was naked eye observation. And of course, it was what he basically could observe from Alexandria through the course of a year. So, I mean, see quite a bit, but of course there was a good portion of the sky that was never available to. The planispherium, simplification of the sphere. This is where, a lot of his work was based on, the spherical representation of the sky, and being able to lay that down into a plane, lay that down onto a piece of paper and model it accordingly. I mentioned before, keep in mind Canopus. This was actually a location, a town, a city. I'll call it a town. I suspect it was just west of Alexandria, but it was on the far western end of the Nile river delta, just as it emptied out the Mediterranean. And this was an inscription that Ptolemy was responsible for at some temple. I'm not sure which one. I'm going to assume it was probably a Roman temple. But basically an inscription that he left. And here again, it's not necessarily at the end of his life, but probably at the peak of the work he was doing at the time in astronomy. And I'll just leave the quotation. This is the quotation on the inscription. Of course, this inscription never survived in this temple. Whether or not this temple was destroyed due to military action, flooding, earthquake, but it was no longer there. This was something that was supposedly transcribed from the original source back in, I think, about the 6th century, and held over and was documented from that time. Later contributions, and this is probably one of Ptolemy's latest works in astronomy, the planetary hypotheses, and actually it was more, number of ideas. And of course, this is the one that cements his idea of the geocentric model of the heavens, on the end of the solar system, however you want to look at it. Of course, like I say, it was based on these spheres moving outward from the Earth. All the stars were basically on a sphere, and of course, the individual, the sun and the moon and the individual planets were on their own sphere, moving out from the Earth, nested spheres. And you can see a representation of it in this picture to the lower right, basically laying it out in planar form. And then there were a couple of, I thought there were a couple of interesting data points that Ptolemy had in this piece. But basically, his estimation from the Earth to the sun was approximately 1,210 Earth radii. Well, he was off by about a factor of 20. So you'd underestimate it. I guess that means he was looking at about 180,000 miles. No, that's not right. It would be 450,000 miles. So, and then here again, you look at his radius of the star sphere. He estimated that to be 20,000 Earth radii, which in actuality is just under an astronomical unit and very much off even to the closest star, almost 4 light years in distance. And then one of the final things he had in there, and I don't know if he actually came up specifically with instructions, but he sort of described in some detail about how to construct an orrery, which is basically, I don't know if you've seen them before, but these are models. The current model with respect to basically it could be mechanical. It was generally made of metal, but it would lay out the sun at this correct one, the sun at the center, and all the planets on little arms, and you could move them around and actually set them, and then set it in motion like a clock, and it would actually simulate the motion of the planets around the sun, not necessarily the distances, because we know that the distances can be quite big, even if we have the Earth at the size of a pea. But nonetheless, he described some basic ideas, some basic points behind construction of such a device to model in 3 dimensions the heavens as he saw it at that time. A couple of other areas he worked in. Cartography was probably the second most. You'll see, basically, you can see a map over there to the right, which was pretty much Ptolemy's world map that he dealt with. Basically going from the equator up to just north, up towards the Shetland Islands in the United Kingdom. Not very much out into the Atlantic, probably pretty much just to the west coast of Europe and Africa. And then, of course, it was known that China did exist. However, there wasn't a whole lot of good detail about it. Just some of the the bodies of water immediately to the east of Egypt and Arabia. But anyhow, like I say, his second most well-known work. Basically, he further developed. He wasn't the first one to necessarily do it, but oh, okay, got it. I was just looking at your comment, Doug, about his measuring the radius. Interesting. Okay, but anyhow, going back to his cartography, how to draw maps using geographic coordinates. He wasn't necessarily the first, but he continued some of that work. The most interesting thing about this, specific work was he identified 8,000 different localities. Now that doesn't necessarily mean towns or cities. It could be, I don't know, an oasis, but 8,000 different localities. A good portion of those 6,300 that actually had assigned coordinates, latitude, longitude. And like I say, for the most part, things were based, latitude was measured from the equator. God, for the life of me, I can't remember where they measured their longitude from at that time. But, they used a common reference point, and so they're able to lay down these points on a sphere and identify them. And of course, here again, using the work of previous scholars, other folks that had already worked in these areas, data. We use a lot of data from previous geographers like Marinus of Tyre. This would have preceded him by probably at least a century. And indices applicable to Roman and ancient Persian Empire, which is just basically information about localities, about places throughout the known world at that time. Okay, astrology. This wasn't something that he was into heavily, but his most well-known work with respect to astrology was called the Tetrabiblios, which is very easily translated to 4 books. Yeah, it's possible his longitude might have been measured from Alexandria, Rome, but for some reason,
capitals of the world at that time.
Yeah, I know, and that makes a lot of sense. But I keep thinking back to some point, and it wasn't necessarily from the prime meridian, but there was some point out west from one of the sources, and I just can't recall it. But I mean, that's being Alexandria or Rome, very likely.
I mean, the prime
going back to the Tetra. Go ahead, Doug.
prime meridian wasn't established until 1,000 years later.
Okay. But going on with the astrology, the Tetrabiblios, here again, there was a lot of previous work that had been done in astrology, and basically Ptolemy took a lot of that work and compiled it in a single source. One of the big differences with respect to Ptolemy's work is, he tried to personalize, the ordering of that information and tried to rationalize astrology. The way he viewed astrology, not so much like people do today. I mean, he certainly saw, I carry this, it wasn't necessarily a quote, but it was a quote from the source, but the physical effects of heavens on terrestrial life. Certainly we know that the sun and the moon have direct physical effects, and they were certainly aware of that during this time. And certainly those two bodies had very significant effects, on terrestrial life. Not so much the other planets or the stars, other than how they're perceived. But one of the things, like I say, Ptolemy, he tried to rationalize astrology a little bit more. He didn't look at it necessarily as a means of predicting human behavior or events, which people put a lot of stock into with respect to astrology and have for long periods of time. But rather, he was trying to look at the actual physical effects that the heavenly bodies had on life on the planet. That direct scientific or objective cause and effect. And that's basically it. These are the sources that I had. Didn't get into a whole lot, but the sources that I used. And like I say, I certainly thank you for your attention. Any questions or comments, please?
That's the most information I've ever seen of Ptolemy in one place.
Oh, really? Well, like I say, there's not a whole lot about the individual himself, and it's more so about his works. I mean, there's a lot more data on the works, but that really gets down into the weeds. I think it covers, the main thing. Like I say, it was his primary works were astronomy and cartography. Those were his main areas, more so astronomy. But certainly, he was, not necessarily the developer, but very much. And like I say, that's held for 1,500 years. The geocentric idea of the heavens.
So, Pete, do you remember that presentation I did last month on that mural, The Man in the Universe?
Yes, I do.
Do you remember at one point I talked about the destruction of the Library of Alexandria?
Yes,
And then
yes,
there was an Arabic figure in there, and I said that represented how the Arabic world continued to advance the science, even though the Library of Alexandria had been destroyed. Well, Ptolemy is a perfect example of that.
as far as what, his information being,
Well, I mean, he continued to advance science and stuff while the rest of Europe was in the Dark Ages and the library had been destroyed, and he carried on.
when was the library destroyed again?
I don't know the exact date, but it was destroyed about 10 years before Julius Caesar was assassinated.
Trying to remember.
It would have been during, it was during the reign of Julius Caesar. Julius Caesar invaded Egypt and invaded the city of Alexandria, and the Egyptian troops laid siege to the city. And during that siege, the library got burned to the ground.
It was rebuilt to some degree?
Yeah, some of the works survived. I mean, there were firefighting efforts, of course, to try to preserve it, but you know, back in those days, very primitive firefighting.
Based on what you told me, though, I think that the initial destruction preceded Ptolemy, probably by close to a century.
50 years.
Yeah.
Yeah.
Okay.
It'd be around 45 BCE,
Okay, so yeah,
somewhere around there.
so at least almost 100 years prior to the peak. Of
Almost
his work
200
at that time.
years. Yeah, but
I think-
he's the epitome of the Arabs carrying on with the knowledge, even though the rest of Europe was in the Dark Ages by that time.
Well, I think that's one of the reasons why you see a lot of star names. You look in atlases and whatnot, carry Arabic,
Yeah.
Arabic derived names.
Absolutely.
I mean, that's very common. You know, if I, you know, as I've gone through my programs, you see that all the time.
Absolutely. That's exactly why they're like that.
I have a question.
Yes,
Go
Kevin?
ahead.
You know, when you talk about these fellows back in ancient times who do work in astronomy, and especially considering that they were basing it on a geocentric model, how do they go about predicting eclipses? What I mean, they have mathematical ideas, but
Okay, Kate, so think about this. If you do the analemma, for example, okay, you can get all of the elements of the orbit of the Earth around the sun. You can get the eccentricity of the orbit, the tilt of the orbit, the tilt of the Earth. All of that information comes out of the analemma. But wait. The only difference is between now and then is when they did it then, the information they thought was the information about the sun's orbit around the Earth. The orbit is the same. It's just a change in reference, okay? The orbit is exactly the same if you think about it. And if you're on the Earth and the sun is orbiting, all the elements are exactly the same. Semi-major axis, the eccentricity, all of it, the period, all of it's the same. So you can use that same orbital information, and you get the same orbital information for the moon. You can predict eclipses.
Except there's, you know, Kay, you raise a good point, because there is one area of this that does cause problems, and I'm sure they identified then, because for the most part, the geocentric, and even if there had been a heliocentric, a lot of these astronomers back then, I think Ptolemy did the same thing, based everything on circular orbits, which we know now with respect to the moon,
That's
it's
true.
very circular.
But you
But
can,
when you start looking at the
they,
sun, you know, you look at the sun-Earth
Ptolemy had
relationship.
figured out the epicycle thing, you know, to
Yeah,
make the orbit. Very
right. The
complicated.
epicycles is what he used to modify that.
Right.
You know, with respect to the Earth and Moon, yeah, it's fairly circular.
It's
And like Doug said, your reference
It
point,
works.
whether you're on the moon or the Earth, it looks like one's going around the other. And with respect to mathematical data, it would hold. The epicycles were used to explain the anomalous planetary behavior,
Right.
one, for the outer planets and the retrograde motion, and then also the fact that these were not circular orbits with respect to outside the Earth-Moon system. Even if, you know, the Earth had been the center, you know,
And
that would have
the
been the case.
epicycle stuff if it's done correctly, actually works pretty good at predicting the motions.
You know, they weren't perfect, you know, they realized they weren't perfect. I mean, it was acceptable. They were still off a little bit,
Yeah,
but they had the general idea. And I think it's a matter of, you know, how precise did they want to be? And I think that they were somewhat aware that they weren't that precise, but they didn't necessarily fudge the data, but they did a little bit, but they found a way to make it work.
the
And it
math
still
works.
fit. What's that?
The math works.
Yeah, the math works, and you know, it fit close enough. It wasn't perfect, but it was close enough at the time. And of course, later on, as you get to the Middle Ages, you know, some of these individuals realized that, well, the Earth wasn't the center of the universe, and they started to identify the weaknesses in some of this work that had been done. You know, basically, you know, remember Ptolemy's work held for 1,500 years.
Yeah,
And part of the problem was a lot of the people during that period really didn't, you know, there weren't a lot of mathematicians running around. There were very few people. And whether or not, you know, it could have been contradicted. I suspect that it probably was, but in this cases, a lot of those works never survived. You know,
well, you got
especially
into
out
the
of
Dark Ages, and you got into the bit where the geocentric model was blessed by the church, and if you dared say that that wasn't true, you got staked to a post and burned. It was considered heresy to say that the geocentric model was not right.
Did that somewhat answer your question, Kay? It's a little bit of a convoluted.
In other words,
answer.
that they figured out the math and it worked.
They made them, well, they made the math work, basically.
Yeah.
And remember, the math here was basically trigonometry.
Yeah.
You know, and that was the most, and you know, they realized that things didn't quite work out, and that's why, you know, one of the things that Ptolemy discussed were these epicycles to explain the anomalous motion of especially the planets that didn't fit the model real well because of the non-circular nature of the orbits, and the fact that on the outer planets, Mars and Jupiter, you know, you get into retrograde motion because they're outside the Earth's orbit, and they're going to look like they're going backwards for a while. So, well, thank you, everybody. Turn it back over to you, Connor.
Good presentation, Pete.
Thank you, sir.
And we're actually just going to transition straight over to Doug in that case.
All right.
That groan almost sounded like you just didn't want to talk for another 5 minutes there, Doug.
No. I just have to
Poking fun at you.
share screen thing. Okay. I hope this works. I've also, oh, I got that too. Good. I'll have to switch at some point. Okay. That's not in presentation mode yet. Okay. Oh, something else on my screen. Let me get rid of something here. Why does it do this every day? Okay. Okay. Does everybody see that?
Yes, sir.
Okay.
Yes.
Okay. So we're going to talk about lunar craters. I always have my comedy. Here's Haley looking for his comet. Okay. All right. So anyone who's ever looked at the moon, even with a pair of binoculars, has obviously seen that it's covered with craters. I'm going to go through and look at some of the more interesting craters that are really good targets to look at if you haven't looked at them before. I'm also going to give a little bit of a brief rundown of how craters are formed and what sort of features you could look for when you look at craters, types of things that you might see. So here's a pretty good diagram of what happens when something like a meteor strikes the surface of any planet, but we're talking about the moon. So initially you get your projectile, your meteor. It starts to penetrate the surface of your planet or moon. And as soon as it starts to penetrate, it starts creating shock waves in the material around where it first struck. As it penetrates deeper into the crust, all that kinetic energy, and there's a lot of kinetic energy, these things could be traveling 100,000 miles an hour relative to the body they strike. All that kinetic energy literally usually vaporizes the impactor projectile and vaporizes a lot of the material immediately in front of it, around it as it penetrates through. The shock wave begins to go out and down through the surface and through the crust, and that shock wave spreads the material out and throws the material back up. If you take a hammer and pound a hammer into a sandbox, you'll see the sand come flying out in all directions. And that's because the shock wave that is happening there, it's going out through the material. As the shock wave continues to go deeper and deeper into the material, you get a rebound of the shock wave too. Think about hitting a bar of metal, for example, with a hammer. It bounces back. You get a rebound. And if this bounce back will actually uplift the floor of the crater. And if it's a big enough impact event, the shock wave will actually tend to concentrate towards the center of the crater. And that's what forms your central peak, is it uplifts material right into the center and you form a central peak. And then the material that was thrown out forms an ejecta blanket that it's called, that falls back down in a radial pattern around your crater. Now, if it's a big crater, you can have a situation where the walls of the crater are very steep. Look at the little picture up there on the right. That crater has very steep walls. And all of this material around the crater has been severely shocked, fractured, broken up, and is not very solid, for lack of a better way of saying it. And oftentimes in large craters, if it's a large enough impact, the crater walls will collapse. You'll get these landslides where the material will slide right down and you'll form a landslide on the bottom of the crater. See if I can get in this area, you can see the landslide material that flowed out, and you'll get these terraces all along the rim of the crater where this part of the rim has slid down here. It has to be a pretty good sized crater. You won't see this in a small crater. For example, meteor crater up by Flagstaff does not have this effect. The walls did not collapse. It's not big enough. But in craters on the moon, where you're often looking at craters that are 50 miles, 100 miles across in diameter, you'll see this a lot, almost all the time. Only in small craters will you not see collapsed crater rims and landslides on the floor. Okay. So the first crater we're going to look at is Copernicus. This is one of the most prominent craters on the moon. And it's often referred to as the model crater. It's got all of the classic features of a large impact crater. And if you look at it, it's got central peak that's broken up, but it's got a central peak here. It's got the terraced walls where the collapsed walls happened, lots of collapsed walls. Here's the material, the landslide material that flowed out across the floor of the crater. Here's the ejecta blanket around the outside, the material that fell back down. Okay, and Copernicus is a very young crater. It has a very large ray system that's very obvious during full moon. You can see it down here in this image. The rays go out in all directions. Typically, the rays disappear after about anywhere from around 1 billion years. The rays are gone. If the crater is older than 1 billion years, you probably don't see rays. And that's from micrometeorite erosion. The surface of the moon is constantly being bombarded by micrometeorites, and eventually the rays, which are very young, very bright material, they will get wiped out by micrometeorites, so you won't see them anymore. And that will also wear, the micrometeorites will also wear down all the features of the crater. So over time, the crater won't look nice and pretty like Copernicus. It has very fresh features, very sharp features. Everything looks, this is a young crater. So, and this is a good target for amateur astronomers to look at because you get a really good view of it. You're almost looking straight down. It's near the center of the moon, and you've got a really good view of it. It's not an oblique view. It's not near the rim. It's a really good view of it. Then, of course, there's Tycho. Tycho is probably the most prominent crater on the moon, certainly the brightest, one of the brightest. And you got a little bit of an oblique view of Tycho. If you look down here, you can see it's kind of oblong shaped because it's closer to the rim, so you're not looking at it straight down anymore. But it has all the same classic features, just like Copernicus. It has the slumped crater walls and the landslides on the floor of the crater, and a thick, heavy ejecta blanket all around the outside here. And it's got a really good central peak, a nice sharp central peak in the middle. And it has the most extensive ray system on the moon. It's very easy to see during a full moon, obviously. And it's a very young crater, probably only 100 million years. Copernicus is 800 million years. So Tycho is very young. And we go to the opposite extreme. Now we're looking at Clavius. And Clavius is pretty close to Tycho. Tycho is right there. Copernicus is here. And Clavius is just beneath Tycho, right here. Clavius is an interesting crater. It's very old. It's one of the oldest craters you can look at. It's 4 billion years old. And it's also one of the largest craters on the moon that did not form into a mare, a sea. The larger impact basins like Mare Orientis or Mare Imbrium, for example, were formed by impacts, but they were formed by impacts that were larger than Clavius. Clavius was not quite large enough to form an impact basin, but it's close. If it was much larger, it would have formed an impact basin, and it would be totally flooded with lava, and it would be dark like the other seas on the surface of the moon. It didn't quite make it that big. But if you take a look at Clavius, you can tell it's a very old crater. First of all, it doesn't have any rays. Secondly, it's worn down. There's not much left of it compared to Tycho and Kepler. You can see that the walls are pretty worn down. You don't see much left of landslides on the floor. It's got a flat floor with almost no landslides. You can't see, you can see a couple places where the walls have collapsed, but most of that's almost gone. And the floor, the crater, is heavily pockmarked with other craters. So there's been a lot of meteors hitting it since it was formed. It is a really good target for amateur astronomers. They love to sketch it because of all the interesting features on the floor and around it. It makes for good sketches and good images. In fact, if you go to the Astronomical League website, the first thing you see when you look at the Astronomical League website is an award-winning sketch of Clavius. This is one of my favorite targets, Plato. This is one of the easiest things to find on the surface of the moon. Very recognizable target. It's sketched a lot and imaged a lot. I've imaged it personally, I've sketched it. And the main reason amateur astronomers love to sketch it and take pictures of it is the shadows. It casts these wonderful shadows. As the sun changes the angle, these shadows change and makes for really interesting sketching and imaging. It's quite challenging though. It's an old crater also. It's 3.8 billion years. It has no rays, and it's still, you can see a little bit of the ejecta blanket around the outside here and around out here. Some of the ejecta blanket is still there, but it's big enough to where it should have a central peak and should have landslides and stuff in the bottom. I mean, it's larger than Tycho and it's larger than Copernicus, so it should have all those features. And at one time it did, but when all of the seas, when all of the major seas flooded with lava, this crater flooded with lava too, and got filled up with lava, so you can't see anything. The central peak and all of the features that were there when the crater was first formed have been buried by a smooth coat of lava. And so it has a very smooth floor. So, another thing that Plato is looked at a lot for is because astronomers, amateur astronomers, have seen what they call transient phenomena in and around Plato. And I'll get to that. That's actually something that amateur astronomers look for when they look at the moon. Plato is a place where that happens relatively frequently compared to other places. Here's my image of Plato that I took with a camera on my 8-inch Meade. And again, you can see there's the nice shadows that the mountains tend to form, all these cute little shadows. But in this image, there's some other interesting things that are challenging for amateur astronomers. There's another, this is called a walled off crater or a ring crater, if you like. Here's another one right here, just below it, just below Plato. Here's what's left of another one that was almost completely covered over by lava when this sea here formed. This crater here, which looks just a little bit bigger than Plato, but roughly the same size, was completely flooded out. There's nothing left, just a bare minimal outline of the rim. And then over here, and there's some ridges. You see some ridges here that are sticking up. But also in this image, which is a challenge to look for, you see some domes. These are domes. These are features that are like volcanic dome type features. And you can tell that by looking at the way the shadow and the light is. The craters have the shadow on the left and the light on the right because the sun is off to the left in this image. But these dome features are reversed. The light is on the left and the shadow's on the right. So they're rises, they're little domes that are sticking up, little hills. Those are a challenging feature because you can tell they're really small. And this is my absolute favorite target, personal favorite, Theophilus and Cyrillus. These are a pair of craters. They're over here in this part of the moon over here. The interesting thing about these two craters, besides the fact that it's a nice, this Theophilus is this one here. Theophilus is a really nice, good looking crater, well formed, has all the classic features, central peak, collapsed walls, the landslides on the floor are easily seen. It's got ejecta blanket all around it out here. In fact, the ejecta blanket has practically filled up this crater here, Cyrillus. And you can see this crater is a much older crater. Everything, it just looks worn down. Look at the central peak. It's not sharp anymore. It's very rounded type feature. And it's worn down from the constant micrometeorite bombardment. You can't see much left of the terraced walls, just a little bit of a hint where there's terracing in the walls. There's still some over here. But so that's a much older crater, and it's got blasted when Theophilus hit it. But they make for a nice pair for imaging and sketching. So, and Theophilus is around 2 billion years, and Cyrillus is closer to 3.5 billion years old. So a big difference in age. Ptolemaeus, I hope I'm pronouncing that right. This is another crater that's very similar to Plato. It's a walled plain that was filled with lava. But what makes this really interesting, amateurs love to go after this one when the light angle is very low, when the sun is very low in the sky from this crater, is because here you can see where there were a lot of impact craters that hit in here before the crater got flooded with lava. You can still see just a little bit of a hint of some of these craters. They're called ghost craters. Here's one right here. Okay, and then here's another one over here. And here's another one over here. These little ghost craters where the lava covered everything over, and as it flowed over these craters, there was a little rise that still remained, showing you where these ghost craters were. And so this makes for an interesting target to photograph or sketch at low sun angles to see if you can pick up these ghost craters. The angle has to be really low in order for you to catch these shadows on the rims. So, neat target. Arzachel. This is a favorite target for amateurs. Again, it has all the classic features, as you can see. It's got the terraced walls, the central peak. It's got the landslide debris all over the floor. It's got an ejecta blanket and so on. But here, the uplift was so severe when the rebound caused the uplift of the floor of this crater is actually a bit of a dome. It actually changes in elevation from here to here. It actually is in a dome shape. And as a result, it's cracked. You've got all kinds of these rills, these valleys, cracks, and there's more of them. There's cracks all over the floor of this crater. And amateurs like to photograph it and sketch it, again, when the sun angle is very low, because then you can see those rills. That's the challenge, is to pick out all these different rills in the floor. So, and it's located right in that area, right almost in the middle of the moon.
Yeah.
Now, this one is an interesting little crater. This is a little small crater called Hortensius. It's not very big. And you notice this crater is small enough to where it doesn't have all the features that the large creatures have. It doesn't have a central peak. There's no collapsing of the walls or anything like that. The crater itself is not particularly special. The crater is located right here. It's about halfway between Copernicus and Kepler. Here's Copernicus is there, Kepler is over here. It's located roughly halfway between. The crater itself is not particularly interesting. What's interesting about looking at this area, though, is nearby, there are a number of shield volcanoes. You can see in this picture, here's two of them right here, but here's the same area looking at the shield volcanoes. Here's the crater, Hortensius, right here, but there's these shield volcanoes that obviously formed much later than the crater and much later than this sea that the crater is sitting in. I forget the name of that sea that it's sitting in. But these are fairly new features. And again, you can only see these under the right lighting conditions because they're not very tall. They're pretty good size. They're like shield volcanoes like that in Hawaii. They're very wide. They're 10, 15, 20 kilometers across, but they typically, in altitude, they might only be 500 meters high. So they're very shallow slopes. But this is an area that's known for having a lot of these shield volcanoes. There's like 8 or 9 of them nearby this crater Hortensius. And then, of course, there's Kepler, which is this bright crater over here. Kepler has a really bright ray system. It's a very young crater. I couldn't get an exact quote for how young, but it's probably actually younger than Tycho. So probably less than 100 million years. And it has huge, compared to the diameter of the crater, huge collapse of the walls. This whole side of the crater collapsed. It's got a central peak. And I think if the lighting came from the other direction, you'd see that this side also is heavily collapsed and terraced. Again, it's a good target to look at. Aristarchus. This is the brightest albedo feature on the surface of the moon. Even when the moon is just lit by Earth light, like in this picture here, it's real easy to see. There it is, right there. This is the brightest feature, which means it's probably one of the youngest features, okay? Because even Tycho and Copernicus and other craters like that, they're very young. But even so, the interior of the crater, if you go back and look at this guy, for example, the floor of the crater is not that bright anymore. It's been darkened by the micrometeorites striking and have darkened it down a bit to where it's not as bright as that. This thing is really bright compared to the rest of the surrounding area. And the micrometeorite bombardment has not eroded it away. Very sharp features, very young crater. It's, like I said, it's the brightest single albedo feature right there on the surface, easily visible even on an Earth-lit moon like that. The other thing that's interesting about that makes this a popular target is there's a really neat valley nearby. Here's the crater, Aristarchus. There's this neat reel right here called Schroeder's Valley, which is a favorite target for imagers and sketchers, right next to it. this is an amateur image here, as a matter of fact, this one right here. People love to take pictures of Schroeder's Valley. That's always a challenge to see. You have to get the right lighting conditions, low sun angle and stuff. And here's a little crater called Marius, which is up here near the rim. The crater itself is not a particularly interesting crater. It's a wall plain like Plato, again, where it was flooded with lava. But all these little hillocks around here are shield volcanoes. This was a volcanic region right around here. Lots of them. You can see at least 20 or 30 of them in this picture. And so those are an interesting feature to go look at. There's also lots of lava tubes in this area. You can see some of them. There's rills. There's a rill in this case is probably a collapsed lava tube. There's lava tubes all over the place. And this area is where they found some of what they call windows, where the lava tube, part of the ceiling, not the whole ceiling, but part of the ceiling collapsed, leaving what amounts to a sinkhole. That's exactly what it is. That's about, you can't see them in this picture and they're too small to see with your telescope, but they were discovered in this region. These areas where a 50-meter or 100-meter diameter sinkhole was formed, where the ceiling of a lava tube collapsed down into the lava tube, and you've got this deep well-like hole that goes down perhaps 500 meters or some distance down into the lava tube. And these are areas that they said could be places where you would build a lunar habitation, because here you've got a ready-made well down into a lava tube underground where you could build a habitation area and you'd be protected from the radiation by the roof of the lava tube. And so they found several of them in this area because there's so many lava tubes. So this was a volcanic region. This is an interesting area to go look at. And this is another one of my personal favorites, Cassendi. It's down here in this area. It's just a really cool looking crater to me. It's got some interesting features. It's got your central peak, and it's got you can see some of the terracing of the walls and some of the landslides. But here it was flooded with lava partially. The whole crater was not completely filled, but you can see where some of the lava that I'm losing my mouse. Some of the lava from this sea down here broke through the wall and started flooding the crater. And so it's an interesting crater. Here's somebody's sketch, not mine. Somebody's sketch of it. So yeah, it's a good sketching crater. One of the things that I always thought makes for good sketching craters is you see these features like this escarpment here, this cliff here, and you got this crater up here, which is kind of cool. And it makes for the sketch looking more dramatic if you see things like that. So it's kind
Hey, Doug, I have a question.
Yeah, go ahead.
Any idea when you look inside Gassendi, especially off to the central peaks there, you see those little striations, or they rills?
Those are rills, yeah.
Yeah. And
Here you get this is another situation where the crater floor is actually kind of a dome. It actually changes in elevation.
oh, okay.
It cracks. And you get the rills formed from the rebound back up and can cause the floor to crack that way. And that's what you're seeing here. Yeah, that you see that in some of the craters, not all of them. So, yeah. Now, 1953, November, An amateur astronomer was taking an image of the moon on film. Here it is here on the right. And he saw, and he captured this in the picture. Turned out that was a meteor hitting the moon. That was the exact second that the meteor struck the moon, causing the fireball that you see where that all the ejected data is being thrown up into space, and you get this bright flash that only lasts a couple seconds. And he was lucky enough to catch it on his picture. And that was the only known case of an observation of that for, I don't know, 20, 25 years. But then people started looking at the moon with digital cameras and started looking at the moon on a more constant, continuous basis. And we've started to see more and more of that happen. Here's another one. And this happened during an eclipse. Look at that. During an eclipse, somebody got lucky. And then here's another one that happened during an Earthlit moon. Okay, you see these meteors striking the moon. And now it's been common practice. Now it happens all the time now. People are monitoring the moon during eclipses, during Earthlit phases, where most of the moon is being lit by Earthlit, especially during known meteor showers. If you think about it, when the Earth goes through a stream of meteors or leftover debris from a comet, and it goes through this stream of meteors every year, well, the moon's going through that stream of meteors too. So it's bound to be hit by meteors, just as the Earth is struck by meteors when we go through a meteor shower. So this is something that happens all the time. Yeah?
Doug, so if I happen to be watching the moon some night and some meteor hit, and then I can get in and it's a sufficient enough hit that I can actually resolve an image, a crater, will the IAU accept my name for it?
Well, I don't know, because these, like this
I know it's
one
probably,
here,
it would be too small. It would have to be pretty
Well,
substantial, probably.
this one here, this image here, they found the crater.
Okay.
They went and they looked with the lunar orbiting satellites, and they found the crater, 1.5 kilometers in diameter.
Yeah,
You wouldn't see that with a telescope. That's
yeah.
too. Well, maybe you would. I'm not sure. Depend on the scope. But these are not going to be big craters. These are going to be small craters. But if you were the only one who observed it and you had the observation, I don't know. They might let you name it.
It'd probably have to be something substantial where you could be able to, where you'd be able to see.
They don't normally name craters that small.
Yeah, I know. I get
It-
that.
Those are considered satellite craters. They're usually named after the largest crater that's close by, and then they give them a letter designation like
Right.
Tycho A, Tycho B, Tycho C, stuff like that.
If it was a large asteroid that would cause a very large crater, I'm pretty sure we would hear about it well before it hits the moon with all the media going, we're all gonna die.
Oh, yeah, that would probably be a near Earth asteroid identified before it got close to the moon.
Yeah.
Yeah.
But this has been common practice now where people are monitoring the moon during Earthlight and during eclipses and, any chance, and especially during meteor showers. In fact, I know I was reading that there's some observatory that has a telescope that does nothing but monitor the moon during meteor showers. They just point it up there and they got a video camera and they're just rolling all the time. Yeah, so that's something that you can do out of the ordinary, a little bit different, and watch for meteors hitting the moon during a meteor shower. And now let's see, I gotta break away from this for a second. And I got something here. Can you see this? Can everybody see this?
Now, still seeing your previous slide, and
You're not seeing my oh, let me Maybe I gotta change the share screen to the other window. Let me try that.
Yeah, you have to reshare, I think, to show
Okay.
another object.
Let me reshare. How do I reshare? Okay, let me
You
stop.
you have
Yeah.
to stop the Zoom share and then
Stop
restart it again.
share
Yep.
and share again. Okay.
Yes,
So
sir.
there was something I want to show you. This. Okay. You got that?
Just about. There you
A
go.
bunch-
Yep.
A
got it.
bunch of pictures. Okay.
Yep.
I got a really cool video here that I found. So here's a video showing a meteor impact on the moon. Look there.
This is from
I don't know where it's from. I couldn't find the source, but
it's
someone
9 p.m. something. Looks
Yeah,
like
some-
1981 from the middle
Yeah.
number.
So somebody's got a video camera looking at the terminator of the moon, and they caught a meteor impact, and you can see the cloud of gas coming out right there. See that?
Oh, okay. Where your cursor is.
Where the
Yep.
cursor is.
Oh, wow. That's not okay.
Yeah. Bang. See that? They caught it. So that's kind of cool. Okay, let's go back to the other one.
Oh, he's got it in a 5-second. That was a 5-second loop. Wow.
Yeah. Okay, where's my, uh-oh. I lost my other one. Here.
But I have a question for you.
Yeah.
Could you see something like that on a full moon, do you think?
No, you probably wouldn't see it on the full moon. You pretty much, I mean, if you look at all these pictures, you pretty much have to be in a part of the moon that's dark.
Yeah.
Otherwise, you're just not going to notice it.
Right. Okay.
Yeah. I suppose if it was big enough and bright enough, you'd notice it. I mean, there is an example back in about 500 years ago, a bunch of monks in Germany recorded or described what turned out to be an asteroid collision with the moon. They saw a huge pillar of fire come out from the rim of the moon, and then they saw the moon turned very dark. The moon vibrated and shook in their description. They said it vibrated and shook. And then they said a large dark mass covered the face of the moon. And where the pillar of fire was coming out, they saw sparks. And well, you know how monks are describing things. It turns out there is a crater called Bruno, which is right on the rim of the moon, right where they described the collision as occurring. It's a big crater. It's like 60 kilometers across. And you can actually see it during libration, once or twice a month when the libration is at the right point. It's actually visible. And the professional astronomers who study the moon looked at that crater with lunar orbital and all the other satellites that they have, and they came to the conclusion that yes, it's a very young crater, perhaps as young as 500 years. And also the seismometers on the moon that were left by the Apollo astronauts still measure vibrations, and the moon is still shaking from that collision. And they measured the vibrations in the moon using the seismometers, and there's the right amplitude and the right everything for a collision to have occurred about 500 years ago. So some monks in Germany probably witnessed an asteroid collision.
That's
And in
kind
a
of
case like that, obviously you'd see it. Something that large, you'd see.
that's kind of crazy that it had imparted enough energy to the moon to leave a detectable energy wave after 500 years.
I know it's not much, obviously. It's probably
Yeah,
very,
it'd be very
it's
small, but that's
measurable.
still a lot of energy.
Yeah, well, think about it. It had to be a pretty huge rock to leave a 50-kilometer crater.
50 kilometers. That'd probably be about a 3-kilometer asteroid, just recalling from basic, some
Yeah.
basic asteroid measurements of impact craters on Earth that I know about.
That's
Be at
a
least
good sized
least-
rock.
3 kilometers could be a good estimate for that.
Yeah. And it would create a large, I mean, the ejecta, the dust and the ejecta that would be thrown up by an asteroid collision that size would cover the moon. It would darken the moon for a period of time. You know, looking at it from the Earth, you'd see it covered up by this cloud of debris that
I
would
wonder-
eventually settle down. But
I
For a
wonder if
while.
any of the debris from that rock re-entered Earth's atmosphere.
that's very possible. You gotta believe that some of the stuff that was thrown off with escape velocity.
No way, our luck, it probably all went in the Pacific Ocean if it did. Good luck finding it.
Who knows? 500 years ago, you don't know. So, but that I read that note. That was a bunch of monks in Germany saw that. So, and then the other thing that people look at, I mentioned this before, it's what's called transient lunar phenomena. And this is where you look at something at a crater, or you're looking at a rill or a valley, and something looks different than what you remember. The lighting is different or something like this. And here's some actual photographic images of what you're talking about. Here's a crater photographed at one point in time. And here it is again, photographed at another point in time. Same camera, same telescope, everything else. There is a difference here. Notice that? Right there. And then here, same crater. And later, they get this in the picture. Okay. And it turns out in this crater, there is a rill right here, cutting right through this area in the floor. Now, what they think this is, for the most case, is outgassing. There's still pockets of gas in the moon, okay, on the rocks, under the rocks. There's still radioactive materials in the moon that are probably producing radon, for example. And you've got other gases and things in the moon still left there in pockets. And once in a while, you get this outgassing from these places. Oftentimes, the outgassing comes out of the valleys, the rills, places where the surface is very fractured. I showed you a couple of craters, Aristarchus, where there's a fractured, where that fractured floors, or some of the other craters that have fractured floors, where you see these kind of outgassing events. And professional astronomers have been seeing this for hundreds of years. I mean, this is not just something recent. Some of the greatest professional astronomers have seen this and they noted it, and it's been captured on, like I said, here's some photographs, and it's been sketched, and this is something you can look for. Certain craters are hotspots for this kind of outgassing, and
I got a question.
they like to go back and look at them. Yeah, go ahead.
What about, is it possible to garner a spectroscopic image of this outgassing?
I'm assuming yes. I couldn't find one.
Yeah, 'cause
But
I think
I'm assuming if you have.
that'd be the
have
next step to solve the
spectroscope-
mystery, I
I
would
mean,
think.
these events don't last long.
Right.
These outgassing events, maybe
And
a few minutes.
How big is that one you're probably looking at, Doug?
Well, I mean, this crater is not a very big crater because it's very fuzzy
Okay,
in the picture. So my guess is it's a very small crater blown up a lot.
but this
Okay,
was something that's probably imaged by a telescope, not an orbiter, correct?
correct.
Okay.
These are images through a telescope, where somebody got lucky and liked looking at the same crater over and over again and got lucky and caught a couple of images of something.
Any idea how old the images are?
I couldn't find out the
Okay.
information.
Just curious. Thank you.
But it's been, I saw a map of outgassing events that have been recorded, and there are literally hundreds of them on the surface of the moon that have been recorded, scattered all over. And like I said, there are certain craters that are hot spots, and I think I can, Gassendi is a place because of the fractured floor, and Aristarchus they've seen them there, especially around where they see them on Aristarchus is a lot of times, let me get back there. The outgassing events seem to happen around down here, around this little crater down here that forms the end of Schroeder's Valley. This is a known hotspot for outgassing events right in this area. And then as I told you, I think I mentioned Plato, which is weird because Plato you wouldn't think would necessarily be a hotspot. But it's known to be a spot where outgassing events have been seen. So, so some amateur astronomers spend a lot of time looking at these areas just to see if they can catch an outgassing event. So, yeah. And that's the end of my presentation, folks. Any other questions?
Bravo, bravo, interesting.
Thank you, Doug.
Yes, thank you.
And before we go, if I can find the right button, there is one picture I do want to share, continuing on the theme for from the moon. So this is a picture that was posted online earlier this month.
Cool.
Yeah, I know I saw that, but I didn't
Yeah.
know where I could fit that in.
Yeah, I still wanted to share it though because it's just such a cool picture.
Interesting. I think the colors represent different minerals or something.
Yes. So
Yeah.
the red is representative of iron and feldspar. The blue areas that you see are representative of oxidized titanium.
Mm,
Oh, wow.
Hmm.
That I didn't know.
At least according to the description, which I am double checking to make sure I read that correctly. Yeah. So the reddish tones demonstrate areas rich in iron and feldspar, while the bluish areas are spots where the regulus is rich in titanium. And oxidation from influence from the Earth's atmosphere makes the colors appear slightly as they do. So this is very much color enhanced. But just because I do a lot of imaging when the sky isn't cloudy for 3 months on end, this is a 174 megapixel image.
Whoa.
So to give you an idea of how much zoom is in this, I'm going to just click here and you get a little bit of distortion in this. You can kind of see it's a little bit distorted. I'm not sure if this is from the focus of the camera that they were using, or if it's atmospheric distortion from their seeing conditions, but it is quite, and I'm not in a good viewer to drag around and show off some of this. I'm just showing this off in Chrome.
Oh, wow. Nice picture.
Yeah. They used the same technique that is commonly used for planetary imaging. So they actually just did a planetary image camera over the whole surface of the moon, came away with about 200,000 individual frames, and then spent a long time putting them all together.
Wow,
Wow.
very good.
200,000.
If you would like,
That is Copernicus.
and I'm going to throw, if anyone wants to go down and stare at this on their own later, the link to the image itself is being thrown in the chat. So if you guys,
Thank you.
if anyone wanted to download that and go stare at it and drag around and see what other interesting things they might just be able to find from this really cool image, by all means, go to town.
Thank you. That's really cool.
Yeah, that was a very impressive image. And with that, I'm going to end the recording here.